Welcome to Flink Forward Asia 2024.
Ladies and gentlemen, there will be another last session. We have a last session on Fluss, next-gen streaming storage real-time analytics that will be presented by Mr. Jark Wu as head of Flink SQL and data channel, Alibaba Cloud, Apache, Flink PMC member. So this is for the last one. Please welcome Mr. Jark Wu.
Good morning. I'm the last speaker of the keynote, so I think I will go through my slides quickly so we can have lunch early. I'm Jark Wu from Alibaba Cloud. I'm leading a Flink SQL team in Alibaba. And I have been working on Flink SQL for over 8 years. And in the 8 years, I put a lot of effort in Flink engine to make the streaming analytics easy and affordable. But we found a lot of challenges that it's hard to be resolved just from the Flink SQL side. So we started to look into the storage to make the storage and computer engine together to resolve some problems. So we started the Fluss project since 2 years ago. So nowadays we can see a significant change in that big data is moving from offline to real time. We can see a lot of different use cases and industries is having the real-time evolution to help the business better. And you may feel the technology changes more deeply, that the big data architecture is moving from the traditional hive warehouse to a modern lakehouse architecture, and to now to the Python streaming lakehouse architecture, which is very famous in Flink community and in China. The motivation of the architecture evolution is users want to have more real-time data and to gain real-time insights and to help the decision more quickly. So we can see the data latency is changed from T+1 day to T+1 minute to T+1 hour and to T+1 minute. However, data lake is a technology based on object storage, which is limited to minute latency. But there is still many business that requires second latency, such as the recommendation, advertisement, anomaly detections. So a second level storage is strongly needed in the industry. And we can see, but there is no such a good low latency storage that is easy to use in big data analytics. So what is the most commonly used real-time storage for the big data? It is Kafka, which is most commonly used in nowadays. And Kafka and Flink is the typical architecture to build the real-time analytics nowadays. But Kafka and Flink is not a good solution, because if you are using the Kafka in big data analytics, you will have a series of problems. The first problem is Kafka doesn't support update. And update is a very, very basic feature in data warehouse that you may want to update or fix some data, but Kafka doesn't support it. And Kafka has to store all the duplicate data on the primary key in Kafka. And when the compute engine consumes Kafka data, it will receive the duplications. So computer engine, in order to guarantee the correctness of calculation, computer engine have to do the deduplication before the calculation. And the deduplication is very, very cost a lot. For example, Flink will use the state to materialize all the input data instead. And this costs a lot of money. And every time you consume the Kafka topic, you have to pay the cost again. So this makes Kafka data is hard to be reused by the businesses. And second problem is Kafka is hard to debug, because Kafka is not queryable. And query is also a very foundational feature in data warehouse. No matter you want to do some debug or some arbitrary data exploration, you need to query the data. But Kafka doesn't support it. So there is two solutions. The first one is you can dump the Kafka data into an OLAP system and just query the OLAP system. But it introduced many, many moving parts, and of course it is expensive, and it is hard to guarantee the data and it is hard to guarantee the data consistency between different systems. And the second way is you can query the Kafka data directly with a query engine, such as Trino. But remember that Kafka is scannable, not queryable. So Trino have to do a full scan on Kafka, even for a very simple query. And Kafka doesn't support any data skipping. So it is very slow to do a very simple query. For example, if you want to query a 1 GB size Kafka data with Trino, you may take over 1 minute. So it is, of course, not scalable and not available for large scale data. The third problem is processing historic data. So, also called backfilling. Backfilling is very common in data warehouse. For example, logistics usually requires to backfilling data from things several months ago. But Kafka doesn't support to retain so long data. It usually retains data for a few days. And when you are reading history data from Kafka, all the data will go through the Kafka broker. It will make Kafka broker very unstable and occupies the Kafka's CPU, pollutes the Kafka broker's cache, and disrupts the live traffic. The last problem is networking cost. Networking cost can account the majority of the Kafka infra cost. But when you consume the Kafka data, most cores are not really used. Take Alibaba as an example. 49 cores are not used in more than 20,000 Flink SQL jobs in Alibaba. But you have to read all the data from all the cores from Kafka and pay the 100% networking cost. Of course, this is not very, very efficient. So we can see Kafka have a lot of problems, not update support, hard to debug, historic data processing, networking cost. So this makes Kafka and Flink is not a good solution. So why Kafka doesn't support these features? Is it possible to add these features on Kafka? But we can see that Kafka is designed for streaming events, not for streaming analytics. So every product has its own positioning and strengths. So Kafka is designed to be a black box to store every kind of data from different applications. So it doesn't have schema. It doesn't have built-in schema, but schema is very, very important for analytics. And Kafka stores data in CSV format, JSON, Avro format. They're all raw format. But analytics requires to work on a large scale data, and it requires the ability to skipping data. But raw format is not good at data skipping, and columnar format is preferred for analytics. So we can see an interesting thing that if we draw a matrix, that the left side is operational system, the right side is analytical system, up side is stream storage, and underside is table storage. We can see that operational database and operational streaming storage are all raw format. And the analytical storage like Iceberg, Snowflake both use the column storage. And we can see there is a missing part in the matrix, and that is the streaming storage for analytics. And as expected, it should be a columnar format. So we started a project to fill the gap in the market and want to fix the problems in streaming analytics and for Flink. So we named the project Flink Unified Streaming Storage, and short name, Fluss, which comes from the first letters. And very interesting, Flink is a German word meaning fast, and Fluss is also a German word meaning river. So we hope Fluss can support streaming data that flowing, converging, distributing, and just like a river. So I will go through key features of Fluss. And the first feature is, as expected, it is a columnar string. And so in the file format, we use Apache Arrow IPC streaming format to store the data. Apache Arrow is a very excellent streaming columnar format. We use the Apache Arrow to do the to get a very awesome projection pushdown performance, and meanwhile still keep the sub-second latency for reading and writing. And the right hand is the benchmark for Fluss and Kafka. We benchmarked the read throughput for reading different numbers of columns. You can see that, and the blue line is Fluss, green line is Kafka. You can see that when you are reading less columns, you will get better performance in Fluss. And you can get 10 times reading performance compared to Kafka if you only need to read 10% columns. And also, projection pushdown is happened in the server side. So only the needed columns will be transferred to client side. So the networking cost will be reduced a lot. And the second thing is the updates and changelogs in Fluss, which is a very important feature that is required by Flink and the streaming analytics. So the foundational of Fluss is a log tablet that provides streaming read, stream write as a streaming storage. And on top of that, we built a Kiwi tablet, Kiwi index on that to support high performance update. And the Kiwi and log is just like a string table duality that Kiwi will, the updates on Kiwi will generate changelogs, and changelogs will written into the log. And during recovery, the log data will be used to recover the Kiwi tablet. So you can think, and the Kiwi tablet is actually is a RocksDB LSM tree. So you can think Fluss is it combines the streaming log and the LSM tree together to support large-scale real-time updates. And also, Fluss support partial update, which can be used to enrich write tables very efficiently. And the changelogs generated by the KV can be read directly by Flink and without any deduplication cost, which saves a lot of computing resources. And the KV index we built on top of that can support us to support high performance prime key lookup. So you can use Fluss as a dimension table or called reference table to enrich your streaming data in real time with the Flink lookup join. And we also support the limited query, count query, and point query to make the Fluss queryable and make the Fluss easy to debug. And a very important feature in Fluss called unification of string and lakehouse. You may know the Lambda architecture, which requires to duplicate data in the batch layer and the streaming layer. With the unification of string and lakehouse, it is some kind of kappa architecture, which unifies the data streaming and the data lakehouse. So it can avoid the data to be stored twice in different systems to avoid the cost, to reduce the storage cost. So at the bottom, Fluss maintains a comparison service, and this service will continuously, automatically to convert the Fluss data into a data lake format. And actually, it is just a convert from the arrow file into a Apache file and commit them into a table metadata. So it is very efficient. And the key feature here is called shared data. So the lakehouse storage and the streaming storage can share data with each other. So on the underside, the lakehouse storage can be the history data layer of streaming storage to store long-term and minute latency data. And the upper side stream storage can be the real-time data layer for the lakehouse, which stores the short-term and the second-level data latency, the latency data. And the data is shared with each other and exposed with only a single table. So when users reading the single table, he can use the lakehouse storage as the history data to have a better performance to catch up read. And when you want to batch analyze on the lakehouse data, you can use the real-time, you can use the streaming storage to provide the real-time data within the minutes. So the analyze on the lakehouse can be a truly real-time analytics, analytic on real-time data. And the converted lake table is in open table format, such as Pymon or Iceberg. So your existing query engines, such as Spark, Trino, Starrocks, can directly query or analyze the lake tables on the lakehouse storage. So here is the overview of Fluss, overview architecture. Fluss is a streaming storage built for real-time analytics. Fluss needs to maintain a server cluster which provides the streaming read, streaming write, and the real-time updates. And it leverages a remote storage for data tiering to reduce the storage cost. And underlying it deeply integrated with the lakehouse architecture to provide rich querying abilities. And the core features of Fluss including real-time read-write with sub-second latency and the streaming updates and projection pushdown to have 10 times reading performance improvement. And you can subscribe the changelogs, and you can have lookup queries and the unification of string and lakehouse. So there are many interesting things I want to share about the future plan of Fluss. But I think these three things are most important. And it also tells the relationship between Fluss and the other three open source softwares. The first thing is Kafka protocol compatible. So it can help the existing streaming data to be migrated to Fluss easily. And the second thing is we want to deeply optimize with Flink to build streaming analytics better. For example, we want to support more push-down optimizations and make the rule-based optimizer in Flink SQL into a cost-based optimizer to leveraging the statistics in Fluss tables. And the third thing is Fluss want to be the real-time data layer of Pymon and Iceberg. With the unification of string and lakehouse, Fluss and Pymon can be a Kappa architecture solution to unify the data storage. And I'm very excited to share that Fluss is just open sourced on GitHub last week. So it is open sourced under Apache 2.0 license, and we plan to donate it to Apache software in next year. And it was just open sourced in last week, and we already have over 700 stars, I think. So you can, of course, to visit github.com/Alibaba/Fluss to visit this project, to try the core features I mentioned before. And we will also have a quick start in there to help you download and try the features. And welcome to join the community to contribute code. And of course, don't forget to give the project a star if you like it. And yeah, thank you very much.
Thank you so much, Mr. Jark Wu, for the last one about Fluss. Fluss is the German river. So that's a real-time efficient for analytic and just opened source last week. So please you can visit the project, and also don't forget to visit the GitHub link. We are so excited to see that Alibaba Cloud announced it has open source Fluss on GitHub. You can now welcome to start Fluss GitHub repository today and post your thoughts about Fluss on social media with hashtag Fluss. It's easy, right?